This leads us to step 8, which is to substitute known values into the derivative. So here's where we left off. I'm on step 7, dV/dt equals 6 dH/dt. Again, we're looking at example 1. What that means is the rate in which the volume is increasing is 6 times the rate in which the height is increasing. So if you look at this picture we drew, you can see the spout coming into the tank. The volume is going to be increasing at a rate of 0.3 cubic meters per minute, right? So we know that. And when we came up with the variables and wrote out what we knew, we wrote that dV/dt equals 0.3. So once you've implicitly differentiated for step 7, you can plug in what you know. In this case, we know that dV/dt equals 0.03. Is it 0.03 or 0.3? Let me make sure I got that correct. Okay, so it is 0.3. We can plug in 0.3 in for dV/dt, meaning the water's filling up at a rate of 0.3 cubic meters per minute. And that's going to be equal to 6 dH/dt. Now, if you know some simple algebra, we're trying to figure out the rate in which the height is rising. We can just divide both sides by 6 and be done. Okay, so we're pretty much done now for this problem. Now, it's not always going to be that way as we look at the other examples. But for step 8, you're just plugging in what you know. You can kind of just go back to step 3, when you write out what you know, and just plug that stuff in from there. Okay, so that's it for this example. Let's look at the next example for step 8, which is plugging what you know. Okay, so remember example 2 has to do with the ladder sliding down, sliding away from the wall. We want to figure out how fast the height is dropping of the top of the ladder. This might be important. What if you're on the actual ladder and you're afraid that it's going to fall down too fast and hurt you, right? So there's one easy practical application to it, safety. But anyway, for step 7, this is what we got when we implicitly differentiated 2x dx dt, dx dt being the rate at which it moves away from the wall, plus 2h dh dt, the rate at which it's falling, is equal to 0. So for step 8, what can we plug in that we know? Well, if you go back and look at what the problem gave us and what we wrote out, we know that dx dt is 0.8 meters per second, so we can go ahead and substitute that right into the formula that we have. So we're going to replace that with 0.8. It's moving away from the wall at a rate of 0.8. Well, what's the units? I cannot remember right now. 0.8 meters per second. Okay, the question is there anything else we can plug in? Well, unfortunately, not right now. Okay, we don't really know how far away it is. So x from the wall, and the bottom of the ladder, and h represents how far away the top of the ladder is from the wall. We're trying to solve for dh dt, so this leads us to basically why we need some more steps. We need to figure out x and h as well before we can solve for dh dt. I want to give you a bit of optimism here. Even though for step 3, we don't necessarily know what x and h is. Now you might say, well, why can't we just plug in 1.5? Well, that's at t equals 0. Remember, we're worried about t equals 1. But fortunately, guys and girls, we have a triangle, and we have some information about where it initially was. Because we know its speed, we can actually figure out how far away it is at t equals 1. And since it's a right triangle, then we can then figure out h. So we can figure out x and h in our future steps, solve for dh dt, how fast it's dropping. So that's it for step 8 for example 2. Let's look at step 8 for example 3. So for example 3, if you remember from step 7, we have dV/dt equals 12 pi over 75 h squared times dh dt. We are concerned with how fast the water is rising in this cone as it's filling up at a rate of 6 cubic meters per minute. If you look at what we wrote out, what we know that dV/dt, that rate in which the volume is increasing, is 6. We know that its height is 5. So guess what? We can replace dV/dt with 6, and we can replace h with 5. And now you can see that there's only one variable left, dHdt, which is what we're trying to solve for. We can basically get it by itself, and we will know the rate at which the water is rising. So as you can see, we're pretty much almost done with this question. So step 8 is pretty simple. You're just looking at what you already know and plugging that stuff in. Going to example 3. This one is going to be more involved, okay? And I will explain why. We actually have nothing to plug in, okay? We don't know the rate in which the water level is, the volume of water is increasing in the actual this actual coffee pot. This is example 4, sorry, not example 3. We don't know the level in which it's increasing here, so we can't replace that. We are trying to figure out dHdt, so we obviously don't know that. So there's nothing to plug in, okay? But that's going to lead us again to another step that's important, which is to figure out the remaining variables so that we can solve for the ultimate question. In this case, how fast is the coffee rising in the pot? Right here, when it's when the coffee in the filter is 5 inches deep, and the rate it's falling at a rate of 1 inch per minute. So that leads us to a future step that will be necessary in order to figure out the ultimate variable we're trying to solve for, in this case dHdt. Okay, so that's it for step 8 of plugging in what you know into the derivative equation. Substituting known values into the derivative. In this case, for example 4, there's really nothing you can plug in, so you just have to move on to the next step, step 9, which is what we're going to look at next.